everyone, and this is day 3 of limits. We're going to look at end behavior here. The one thing that you're going to notice is the first two theorems are going to look very similar to the first two theorems of the previous day. We're just going to keep going with this idea of limits in these two theorems. Now, we know that when we talked about the limit as something as x approaches something of k, we know that that's just a straight line, and of course that's not going to work. Let's go here. Let's try this again. We know that we're going to just get a straight line, that being k. And so as we look at end behavior now, end behavior as we go to negative infinity, of course, is going left, and positive infinity, of course, is going right. So I hope it's kind of obvious to you that as we go to the left, we're going to stay at the same number, which is k here. And as we approach the right, as we approach infinity, we still are going to be at k. So those two, the limit as x approaches any constant is going to be that constant because it's just a straight line. Now, we move down to theorem 2 here. We're going to look at the limit as x approaches the end behavior of y equals x. Okay, let's try to make that a little clearer. There we go. Y equals x. Now, as we go to infinity, as we go to the right, where is this approaching? Well, of course, we're going to be approaching infinity here. And as we go to the left, as we go to negative infinity, we're approaching negative infinity. So, I hope that are two theorems that make sense to you, that aren't too difficult. Now, the one thing that we need to remember is what a polynomial is, and we went over this in class a little bit, but a polynomial, a smooth continuous function, it's got a certain degree. And we know that a quadratic, y equals x squared, a quadratic, or y equals x to the fourth, a quartic. Those are all even degree polynomials. It's the highest degree. We don't care what's being added on after this. We don't really care what's ax plus c here. We don't really care about that. All we care about is that the highest degree is even, and we know what those look like. We know those look something like this, or something like this. Now, could there be more maximum minimums inside if it's a quartic or 6th degree? Sure, but we're looking at solely the end behavior. Can either look like that. An odd degree function is going to look something like this. And so the idea based here is the sense that even degree has the same end behavior, and the odd degree has opposite end behavior. And so if it is a positive coefficient, we're going to always have as limit as x approaches infinity always going to be infinity. If it's a negative coefficient, the limit as x approaches infinity will always be negative infinity. So that's important to know. So both the reds, guys, are positive coefficient. These purple ones here are negative coefficients for the leading coefficient. Let me make that clear. The leading coefficient. So red implies positive leading coefficient, and purple implies negative leading coefficient. Just so you guys know that. So as we move on to the examples here, we look at the coefficient. Let's try to look at that. We look at the coefficient, which is 1. So we have a positive coefficient, and we have an odd degree. And so we know that an odd degree positive coefficient looks something like that. And from A2, if you remember anything, I spent a lot of time on this. So positive coefficient, odd degree, that means that as we go to infinity, we're always going to be looking positive since it's a positive coefficient. So we know that that is infinity. We don't care about anything else. We just care about the leading coefficient and the degree. With this one, again, positive coefficient, odd degree, same thing here. We're looking at negative infinity, so therefore we must be going to negative infinity here. Positive coefficients here, both odd. If I had given you something like this, of negative x squared plus 3x plus 1, we know that it's an even coefficient, or even degree, but a negative coefficient, and so therefore we know it would be down, down, so these are both negative, or there would be negative infinity. Both end behaviors would be. Okay? A quick joke for you here. Why should you never talk to pi? What do you think? Why should you never talk to pi? Try to answer that in class. It's a good one. So as you're thinking about that, let's move on to page 2. So the end behavior, as we go to negative infinity of f of x, is 3, and the end behavior as we go to negative infinity of g of x is negative 2. So again, with this, we want to split it up using the same rules that we used last time. And so since we know excuse me, know what that is, we know what that is. We know that 3 minus 4 is negative 1. This is a good one to do here. The limit as x approaches negative infinity of x cubed plus the limit as x approaches negative infinity of g of x. We need to make sure we have our equal sign there. So what is this? Well, x cubed, we know x cubed looks, the end behavior is that. And as we approach negative infinity, we know it's going to be negative infinity plus a negative 2. Well, we know infinity is always win out. There's never a chance. So we know that it's just going to be negative infinity. That plus negative 2 means absolutely nothing. Negative infinity will always win. Infinity will always win. So let's look at this one. Now, 1 over x. We have to know. You have to know exactly what this looks like. It's called the reciprocal function or the inverse function. So as we approach infinity of 1 over x, where is the arrow going to? Well, as x gets extremely large, this gets extremely small. 1 over 1,000, 1 over 1,000,000, etc. So that's going to be really close to 0, and we see that right there as we have the asymptote go to 0. Okay, I want you guys to just try this on your own real quick. So pause the video and try this on your own. See what you can get, and then I'll come back with the answer. So I hope you guys got to this point. The fact that we can, the limit of the quotients of the limit, so therefore we can split those up. We also know that the difference of the limits is the limits of the difference, so we can also split that up. And you should have gotten to 3 over negative infinity minus 2. And this is the key point right here. This 3 over negative infinity. I hope that you can see that if you take 3 and divide it by a huge number, it's the same thing as we did right here, 1 over x. It's going to go to 0. And so therefore, when you get 0 minus 2, we just get negative 2. And this is the idea of the limits, and we're going to use this arrow symbol, it's not usually that long, that it implies that it goes to 0. 3 over a huge number is going to approach 0. And so we can just put that arrow and say 0 and get negative 2. So we use the rules that we learned last time about limits. We split it up. We know that 3 over infinity, we know that 1 over infinity, any number constant over infinity will go to 0. Whether it's positive or negative infinity, it does not matter. And so we're just going to get 0 minus 2. Okay, now what happens though when we get rational functions? We just talked about polynomials, now we're going to talk about rational functions. The idea here is that we need to figure out where the asymptotes are. That's really the idea, is where's the horizontal asymptote. That's what this is looking at. We're looking for the horizontal asymptote. And I'm going to pause the video and show you, it's going to take too long for me to write it out, the proper mathematical way to do it, and then I'll show you the shortcut. Okay, so we took this idea that we're going to divide the numerator and the denominator by the highest power in the denominator and simplify. So the highest power here is x to the first. I divide every one by x to the first. Notice that in the first one, I didn't write it out, but the limit could go to each single one of those. We're going to imply that we know that now. So the limit as x approaches negative infinity of 3x over x. Well, that just goes to 3. We know that. Then the limit as x approaches negative infinity of 8 over x. That just goes to 0 from the work that we did above. 8 over a huge number is going to go to 0. All divided by 6 minus 0 again, that's going to go to 0. These x's cancel. So you're just left with 1/2. Again, if you guys remember back to Mrs. Reed's class, we're looking at the horizontal asymptote. If it's the same degree, what's the shortcut? The same degree, we just look at the coefficients, 3 divided by x. And that's the mathematical way. If you divide by the highest power in the denominator, that's the reason why it works. Again, I'm going to pause this, show it, so we don't run out of time. So with this one, if we have a larger power in the denominator, just messed that up for you guys, sorry. If we have a larger power in the denominator, that means the denominator grows faster, which means we're going to 0. Those cancel, goes to 0. We're left with 0 over 2, which equals 0. Again, which one's growing faster? The denominator in this entire thing, x cubed is bigger. And so when the denominator grows faster, we're going to have an asymptote at y equals 0. And you guys learned these rules last year with Mrs. Reed. Again, pause, and I'll do the same thing. Okay, I'll have you pause it and look at my work. So pause it now, you can look at my work. Hopefully that makes sense. If it doesn't, you can ask me in class. And so now we're going to go on to the limits of radicals. And if that thing will work. So the last little bit that we're going to do is talk about the limits of radicals and the end behavior of them. So look at the steps. Divide by the numerator the highest power. Compute the limit of each individual part. And the sign, only when dealing with radicals, is a symbol of the infinity sign. So with this, the key thing is, if you have x, the equivalent portion of that is the square root of x squared. Why is that important? Well, let's look right here. We have the end behavior of another rational function. The highest power in the denominator is x, so you're just going to put x here. But to make it the same, what are you going to put in the numerator? You're going to divide the numerator, since it's in a square root and we divided it outside a square root of x. Inside must be x squared. Okay, it has to be x squared. Do not forget that. If you have a radical in the numerator and you're dividing by a radical, or dividing by just a regular x, it must be an x squared in the radical. So if we do this, that goes to 1 plus 0. That goes to 0. Doesn't matter if it's in the radical or not. It still goes to 0. Over 3 minus 0. That goes to 0 also. So you're left with 1/3. Why is it 1? Because radical 1 equals 1. Okay, what about this one? Well, same thing here. We're going to divide by the highest power in the denominator. That's x. So what does it have to be inside? But x squared. Inside the radical is to be x squared. So what are we going to get? We're going to get the radical of 8 minus 0 over 3 plus 0. These all go to 0. And so the key thing here is that we're at negative infinity, and so therefore the final answer is negative square root of 8 over 3, or negative 2 square roots of 2 over 3, depending on how you want to deal with that. I don't care. The last part, I want you to pause it, and I'll have the answers after you're done. End of the notes here, we've got square root of 7 over 2. And we have the cubed root of 1/2, and hopefully that makes sense. That should be a 0 right there. I don't know why that didn't come out. And to answer the question, the riddle, why should you never talk to pi? Because pi will keep going on forever and ever and ever, just like me in these videos. Have a good day.